Hello everyone and welcome to the channel. This is part 4 of making a 65C816 breakout board PCB. If you haven't watched part 1 to 3, I recommend you start by part 1 now, as I explain what I'm doing, and I won't be doing it in the intro to this video. In this video, we'll continue routing the physical board to completion and send it over to the manufacturer. I hope you enjoy! In the past video, we've made a first attempt at placing the components and routing the tracks, and that attempt was pretty good, but I think I can make it even better. So I'm going to start again. I will make some adjustments to the component placement and route the tracks again. So let's do that now. Let me delete all the tracks and vias from all layers. And let's start again. Okay, so these resistor networks, I think I want to shift them so that it's nicely aligned. Like so. Same for this one. Like so. And so that means that in my edge cuts, I can make the board a little smaller. And same thing in this side. And this. So I still have a bunch of unused space over here, and I don't really know what to do about it. Ah, I know what I forgot. We need mounting holes. So let me add them. And I'm going to make them grounded. There we go. So because I want to add the two mounting holes in the corners here so they provide good physical support, not sure where to put the power connector anymore. I think here's the best solution. Okay, I think that's as good as I'm gonna get it. Now there's the question of the test points. I'm not gonna be able to route this in a good way because these have to go everywhere. So what I'll do instead is I'll do individual test points. So for my test points, I want to be able to solder wires to them if I want to, and my breadboard wires are 22 gauge wires, and so we can use the through-hole pad with a drill of 0.7 because 22 gauge is 0.6 and something, and I want them to be as small as possible. So I want to change the designator to not visible, and I will move the value to the cell screen. And I'm going to place them as close as possible to the gate that is driving the signal so that it doesn't change the routing too much. Okay, so these are all the test points. So the DS1035M is an obsolete chip. I'm using it because I don't want to use any surface mount chips in this build. However, there is a drop-in replacement that is SMD, and that's the DS1135Z-10. So I have here the footprint for the 1035, but it would be nice to include in the board a footprint for the SMD version, just in case you can't get the old DS1035 anymore secondhand and you have to purchase an 1135 instead. If we look at the datasheet for the DS1135, we can see it's an 8-pin SO package, and if we go down here we can see the package information with the outline, and this gives us the dimensions of the package, and we can see that it is 3.90mm wide and 4.90mm long. In KiCad, we can add an independent footprint of an SO8 3.9 by 4.9 with a 1.27mm pitch. I'm going to try and put this under the footprint for the DS1035, and I will mark this as not in schematic, so that it's not deleted when I update the PCB from the schematic. Now we can say here DS1135Z-10. So now the question is, how do we make this look nice? And the pinout is the same, so I will add the correct net to each pin. And there we go. And now you have a choice to place either the through-hole version or the SMD version. Okay, so one thing I didn't do before I started routing earlier is set up my board properly. So I will use a 1.6mm board. We have 4 layers, and now we have to set up the design rules for the manufacturer. So personally, I will use JLC PCB, and you have to go to their capabilities page to know what to put in the settings here. So for the minimum clearance, we're using a 4-layer board, so the minimum spacing is 3.5 mil. The minimum track width is 3.5 mils as well. And I'm in millimeters here, so let me go to mils here. Okay, so 3.5 mils. And track width is 3.5. The annular width is 0.3 millimeters. The minimum via diameter is 0.4 millimeters. And actually we are going to use 0.45 because if you go to 0.4, it's an additional price. The copper to hole clearance is 0.33 millimeters for a plated through hole, which is the majority of the holes we have in this board. And then copper to edge is 0.2 millimeters. The minimum through hole is 0.2, and the hole to hole clearance is 0.5. And we don't have micro vias. And I guess I'll set up the minimum sizes as predefined dimensions. But I will go with something a bit bigger, I think. I'll go for 6 mils track, 0.6 millimeters vias with a hole of 0.3. And I think that's a bit more reasonable. And I can fit 2? No, I don't think so. I can actually, yeah. I can fit 2 side by side between plated through holes. And I think I can increase this a bit. Still have a little bit of margin, so let me increase the clearance. So I will do 7 and 7. Let me see, does that work? That's good. I can fit 2 tracks beside each other. And I think clearance is more important than track width. So I will go with 8 mil clearance and 6 mil track width. So let me just redo this now with the new tracks. Okay, so I said I will go for 6mm traces. However, I also want to be able to add source termination resistors on some of them, and so I have to know their impedance. For that, I will go to the JLC PCB website, because that's my manufacturer. This is not sponsored, and I will select the JLC 3313 stack up because the ground planes will be closer to the top layers. As you can see, the prepreg here is 0.09 millimeters, whereas here it's 0.21, and so this is going to be better for our controlled impedance. And we can see that if we go to the impedance calculator, let's say we want to route this as 50 ohm controlled impedance on a 4-layer board that is 1.6 millimeter wide on the outer layer and a single-ended signal. It says that for the 7628, the trace width should be 11.55, which is quite big. It would be the double of this one. And as you saw earlier, we have a lot of traces to route, so I'd rather go for the 3313, which has a 5.78 mil recommended trace width. So that's what I'm going to go with. One other thing that we have to pay attention to is the current carrying capability of the trace. And we can use KiCad's PCB calculator for this. If we give it in mils a trace width of 5.78 with a thickness that is dependent on the stack up. Here for the specific stack up, the thickness is 0.035, which is what we have here. We can see that this trace is going to be able to carry a current of around 600 milliamps, which is fine for most of the traces in this build. I don't think this is going to consume a lot of current, maybe a few tens or maybe a couple of hundreds of milliamps. And that's with a temperature rise of 10 degrees Celsius on a pretty short trace. Of course, we have to pay attention that we also have a power output here. And so the current that we draw here is not defined. It depends on the use case. And so it would be nice to be able to carry quite a bit of current from the input to the output here. So I will make this trace bigger, let's say double. And if I do double, that's 11.56. And this will be able to carry almost 1 amp of current, which I guess is enough. So let's do that. I will update my board setup here, and my track width is going to be 5.78 for 50 ohm control impedance. And then in my predefined size, I will add one at 11.76 mils. And that's going to be for my power carrying trace. So just to be safe, we have to redo this one. There we go. And then I will use a pretty big trace to go from VCC here. And I guess that's not actually that big. Okay, so let's start over with the routing. I will start with the buses, just like before, because that's the denser signals. And so let's do that. So I'm going to try to route anything that is vertical in the front layer and anything that is horizontal to the back layer. And that's going to help us with crossing signals. Just realized I have the wrong track size selected. Okay, so this is the buses connected. Let's do the power circuitry. So for the power, I try to route in a star fashion. So I have a few branches going around, and for each IC, I make sure that the power input is first going through the decoupling capacitors, and then the input that I have pulled up in each chip, I take from the chip power supply as well. So I think that is everything in the power routed. Now let's do the clock section, the power LED. So this is the driving point of the clock, and it's the most important signal in this board. Everything is dependent on the clock, and the CPU is quite sensitive to having a good clock signal. So I want to make sure it's routed in priority, and I will go from the driver over here through the termination resistor to the CPU first, and then I'll go to the glue logic on the top right. Alright, so I believe this is everything. Let's verify with the DRC. We're missing A8 here. This one. Okay, everything is connected. And we have a number of violations. So the holes here are too close together. So I have an issue here with all my footprints that I made for the termination resistors. I'm going to ignore this. So there is a clearance problem here. This is fine. And then I have a bunch of errors with my annular width. I think the board setup is wrong. So I'm going to edit the keep out area to allow vias. As long as they're not on the text, it's fine. Okay, and I'll have a look at my board setup now. So I think this was the value for the plated through holes. Yeah, it's 0.13 millimeters. And so this is going to include vias. Let's run the DRC again. It's clear. Awesome. It looks like our zones were out of date, but I'll let it sit for a bit and come back to it later and do some cleanup and checking of various things. One thing I'm considering adding is ground connections at the bottom, because if I ever end up using this as a mezzanine board for a larger PCB, such as the whole computer I'm building, it would be nice to have good ground return path. And if you look at it now, the ground pin is all the way here to the left. So any signal that is here on the right is going to have a huge loop area for the ground return. So I'm going to have to modify the schematic and the footprint assignment. So we have to replace this one and this one by double row versions. And we can connect everything to ground. Now in terms of the footprints, we have to use a pin socket with a 0.1 inch pitch. So 2x40 is this one. And 2x18 is this one. Okay, now let's update the PCB. That's not good. Don't have the right pin numbers. We have to use the odd even numbering. And now if we place it using the same grid, it will work by default. And we just have to extend our board. Okay, so there is one problem, and that is the ground plane is not connecting here to the ground pads. Okay, that's much better. Okay, now one thing we have to do is make sure that nobody is confounding these ground signals with the connectors. So when looking at the board, it seems like it shows the wrong footprint for the header. This is a socket, not a header, so let me fix that. And I also want to add designator to the reset switch and the power LED. Okay, that's much better. So we have more vias to place. Every time I use the via to make a signal change side, I put a ground via next to it. And that is because the signal has to change its ground reference when traversing the board. However, with through-hole components, there's a second place where that can happen. And that's when you change layers through pads. And there as well, we have to put a ground via to help the signal cross the board. So I have to check everywhere in my board. Everywhere I've used 2 different layers connecting to my pads, I have to put a ground via next to it. And then we have to add stitching vias that will connect our 2 ground planes everywhere. And it seems like I've added unconnected vias, and that's because when you do this and you don't have your layer selected, it doesn't understand that this is ground, but if you do it and you have your layer, it will figure it out. So that's my mistake. Now it should be pretty easy to change this directly in the file. And you can see that now the vias are correctly assigned to ground. So we can refill the zone. It will now be connected. Awesome. So I figured out that KiCad actually has a built-in footprint for the DC jack that is better. So I will change this one. Alright, so I think this is a good design. I've been working on this for at least a week now, over a few days, just to let things sit and progressively hone in on the design. But at some point you have to stop, right? So yeah, I think this is pretty good. I'm gonna call this done and send it to the manufacturer. So I leave most options as the default. I use controlled impedance with the 3313 stack up. I want the PCB in blue, and the rest I will leave as default, except remove order number. I have specified the location so that it's under a chip. And yeah, that's everything. So it will come to $40 and $47 shipped, which I guess is to be expected because this is a wide board, wider than 100 millimeters. All right, so I'm pretty happy with this design and also pretty stoked with finally sending it to the manufacturer. Now I have to wait for the board to come back, but once I do, we'll do another video with the assembly and putting it into the circuit. So I'm not sure if this video is going to be next week or the week after, because it all depends on production and shipping. So next week is going to either be assembly and testing of this board, or I have a software video I want to make, adding a EEPROM programmer to my Teensy, so I don't have to pull out the ROM every time I want to work on software for the computer. So we'll see. In the meantime, I hope that you've enjoyed this video. Let me know in the comments if you've got any questions or feedback, and I hope to see you in the next one. Goodbye.